So here's something to think about as you settle in tonight. Right now, beneath wherever you are, whether you're lying in bed or curled up on a couch, there is rock. Solid, stable, reassuring rock. And beneath that rock, more rock. And beneath that, still more. But if you could somehow keep going down, keep drilling through all of it, something would start to change. The rock would get warmer, noticeably warmer. For roughly every kilometer you descend into the earth, the temperature rises by about 25 to 30 degrees Celsius. That's a real number, by the way, something miners figured out centuries ago, because the deeper the mine shaft, the hotter it got. Some of the deepest mines in the world, the gold mines in South Africa that go nearly 4 kilometers down, the rock face temperature reaches 60 degrees Celsius or more. Miners can only work there because of massive refrigeration systems pumping cold air into the tunnels, and even those only go a tiny fraction of the way down. The Earth is about 6,370 kilometers from surface to center. At the core, temperatures reach something like 5,000 to 6,000 degrees Celsius. That's roughly as hot as the surface of the sun. And all of that heat, all of that unimaginable energy trapped beneath a thin shell of solid rock, is what makes volcanoes possible. A volcano, at its most basic, is just a place where the inside of the earth finds a way out. A crack, an opening, a weak spot where molten rock from deep below pushes its way to the surface and, sometimes gently and sometimes with unbelievable violence, escapes into the open air. That's it. That's the fundamental idea. And yet, when you start looking closely at how and why this happens, at what's actually going on down there, at the sheer variety of ways the earth can open up and release its heat, it gets wonderfully complicated and strange and fascinating in ways that people have been trying to understand for thousands of years. And that's what we're going to do tonight. We're going to talk about volcanoes, all of it, why they exist, how they work, why some of them ooze gently and others explode with the force of nuclear weapons, why they're found where they are, and what they've meant for human civilization across all of recorded history and beyond. We'll take it slow. There's no rush at all. And if you drift off at some point, that's completely fine. The volcanoes will still be here. They've been doing their thing for 4.5 billion years. They can wait. Let's start where most good stories start, which is with people trying to make sense of something terrifying. Because if you were an ancient person, living near a volcano, and one day the mountain you've known your whole life suddenly starts shaking and roaring and spewing fire into the sky, you would need an explanation. You'd need to understand why. And without any knowledge of geology or plate tectonics or mantle convection, the explanations people came up with were, understandably, mythological, divine, personal. The Romans had Vulcan, the god of fire and the forge. He lived beneath the earth, working his bellows and his anvil. And when the mountains shook and fire poured from their summits, that was Vulcan at his forge, hammering out thunderbolts for Jupiter. The word volcano itself comes from Volcano, a small island off the coast of Sicily that the Romans believed was one of Vulcan's workshops. It's still there, still volcanically active, and the name stuck. Every volcano on every planet in the solar system traces its name back to a Roman god hammering metal under a Mediterranean island. The ancient Greeks had their own version, Mount Etna, that massive volcano on the eastern coast of Sicily, was said to be the prison of Typhon, a monstrous giant who had challenged Zeus himself. When Typhon thrashed and raged beneath the mountain, the earth shook and fire erupted. Or in some versions, the Cyclopes lived under Etna, forging weapons for the gods, and the eruptions were sparks from their work. Either way, the story served the same purpose. It gave shape and meaning to something that was otherwise simply terrifying. But perhaps the richest volcanic mythology in the world belongs to Hawaii, and specifically to the goddess Pele. In Hawaiian tradition, Pele is the goddess of fire, lightning, wind, and volcanoes. She's powerful, passionate, unpredictable, generous, and destructive in equal measure. The stories say she traveled across the Hawaiian island chain from northwest to southeast, looking for a home, digging fire pits on each island until she finally settled in Halemaumau crater at the summit of Kilauea, which is where she lives to this day. And here's what's fascinating about this particular myth. The Hawaiian Islands really were formed sequentially, from northwest to southeast, as the Pacific tectonic plate moved over a stationary hotspot deep in the mantle. The oldest islands are in the northwest. The youngest, the Big Island, with its actively erupting volcanoes, is in the southeast. The myth of Pele's journey mirrors the actual geological history of the island chain with remarkable accuracy. It's one of those cases where cultural memory and geological reality line up in a way that gives you chills. Now, myths are beautiful, and they tell us something important about how humans relate to natural forces. But at some point, people started asking different kinds of questions. Not, who is angry inside the mountain, but what is actually happening inside the mountain? And the story of how we went from mythology to science, from gods in the earth to plate tectonics and magma chemistry, is one of the great intellectual adventures of the last few centuries. And like most great intellectual adventures, it was full of wrong turns, stubborn arguments, and people who were absolutely right about things that everyone else thought were ridiculous. One of the earliest attempts to think about volcanoes in a naturalistic way came from the ancient Greeks, because of course it did. Aristotle, writing in the 4th century BCE, proposed that volcanic eruptions were caused by winds trapped inside the earth. He thought underground caverns contained great quantities of air that would heat up, expand, and force its way violently to the surface. It wasn't a crazy idea, honestly. If you've ever seen a geyser, or felt the ground shake, the notion of pressurized gas trying to escape makes intuitive sense. Aristotle was wrong about the specifics, but the general concept of pressure building up and then releasing, that's not entirely off base. Pliny the Elder, the Roman naturalist, held similar views, and he would end up paying for his curiosity with his life in one of the most famous volcanic events in all of history, August 24th, 79 CE. That's the traditional date, though some recent archaeological evidence suggests it may have actually been in October. The location is the Bay of Naples, in southern Italy, one of the most beautiful and densely populated regions in the Roman world. And the volcano is Vesuvius. Now, here's a detail that a lot of people don't realize. Before that day in 79 CE, nobody living at the time really understood that Vesuvius was a volcano at all. It hadn't erupted in at least 800 years, maybe longer. The slopes were green and fertile, covered in vineyards and farms. The Roman towns clustered around its base, Pompeii and Herculaneum, and Stabiae and others, were prosperous, thriving places. People lived there precisely because the volcanic soil was so incredibly rich. Grapes grew beautifully. The wine was famous throughout the empire. Nobody was afraid of the mountain. It was just a mountain. And then, one August afternoon, the top of the mountain blew apart. We have a remarkable eyewitness account of this eruption, and it comes from the most unlikely and most perfect possible source, Pliny the Younger. He was 17 years old at the time, staying with his uncle, Pliny the Elder, at a villa in Misenum, across the bay from Vesuvius, about 35 kilometers away. His uncle was the commander of the Roman fleet stationed there, and also one of the most prolific scholars of the ancient world, the author of a massive encyclopedia of natural knowledge. When the eruption began, The elder Pliny's first instinct wasn't to flee. It was to get closer. He wanted to observe. He wanted to understand. He ordered a boat prepared and sailed across the bay toward the eruption, directly into danger. He never came back. The younger Pliny survived, and years later, at the request of the historian Tacitus, he wrote 2 letters describing what he saw and what his uncle experienced. Those letters are extraordinary documents. They describe the eruption column rising from the mountain like a massive pine tree, a tall trunk shooting up and then spreading out into branches at the top. That description is so precise, so visually accurate, that modern volcanologists named that particular type of eruption after him, a Plinian eruption. When you hear that term, that's where it comes from. A terrified teenager watching from across the bay as a mountain devoured his uncle. Pliny describes the rain of pumice stones, light and porous, falling like hot hail. He describes the darkness that descended, not like a cloudy night, but an absolute, impenetrable blackness, as if you'd been sealed in a room with the lights extinguished. He describes people tying pillows to their heads with strips of cloth to protect themselves from the falling stones. He describes the tremors that shook buildings off their foundations, the sea pulling back from the shore and then surging forward. His uncle reached the shore near Stabiae, tried to shelter at a friend's villa, and eventually died, probably from volcanic gases. His body was found 2 days later, intact, looking more asleep than dead, according to his nephew. The destruction was total. Pompeii was buried under about 5 to 6 meters of pumice and ash. Herculaneum, closer to the volcano, was buried even deeper, under roughly 20 meters of volcanic material, much of it pyroclastic flow deposits, those superheated avalanches of gas and rock fragments that race down volcanic slopes at speeds that can exceed 100 kilometers per hour, with temperatures of several hundred degrees Celsius. The people who were caught by those flows died almost instantly. The heat was so intense that it carbonized wood and, in some cases, vaporized soft tissue. Herculaneum was buried so deeply and so quickly that it was essentially sealed in a time capsule, only rediscovered by accident in the 18th century, when workers digging a well struck a marble floor. And here's the thing that connects this ancient catastrophe to everything we're going to talk about tonight. The eruption of Vesuvius wasn't some exotic, one-time event. It was a perfectly normal, perfectly predictable consequence of the geology of that region. Vesuvius sits right where the African tectonic plate is being pushed beneath the Eurasian plate, a process called subduction that we'll get into more deeply later. The conditions that destroyed Pompeii are the same conditions that build volcanic arcs all around the world, from Italy to Indonesia to the Andes to Japan. The Romans just didn't know any of that. They couldn't have known. The intellectual framework needed to understand why Vesuvius erupted wouldn't exist for another 19 centuries. And there's one more detail about the Vesuvius eruption that I think is worth mentioning, because it's haunting, and it tells you something about how people behave in the face of catastrophe. The archaeological excavations at Pompeii, which began in earnest in the 18th century and have continued sporadically ever since, have revealed something extraordinary. The city was preserved in astonishing detail, not just the buildings and the streets, but the objects of daily life, bread left in ovens, graffiti scratched into walls, surgical instruments, dice, even jars of preserved food, and most famously, the casts of the dead. When the volcanic ash buried people and animals, their bodies decomposed over time, leaving hollow voids in the solidified ash. In the 19th century, an archaeologist named Giuseppe Fiorelli realized that you could pour plaster into these voids to create perfect casts of the people as they were at the moment of death. The results are some of the most striking and moving archaeological objects in the world. People curled in corners, families huddled together, a dog straining against its chain, a man covering his face with his hands. They've been frozen in the act of dying for nearly 2,000 years, preserved by the very force that killed them. It's a stark reminder that volcanic eruptions aren't just geological events, they're human events. And every number, every statistic about death tolls and cubic kilometers of ejecta represents real people with real lives, caught in the path of forces they couldn't understand and couldn't escape. But people kept trying, and throughout the Middle Ages and into the Renaissance, theories about volcanoes were, let's say, creative. Some scholars thought volcanoes were fueled by burning deposits of coal or sulfur underground. Others thought seawater was seeping into the Earth's interior through cracks, hitting hot rocks, and flashing to steam, which then drove eruptions. That second idea, by the way, isn't entirely wrong for certain types of volcanic activity, but as a general explanation, it falls apart pretty quickly. The real breakthrough in understanding volcanoes wouldn't come until people started understanding something much bigger: the Earth itself, what it's made of, how it moves, and what, exactly, is generating all that heat deep down inside it. And that understanding would take centuries of patient observation, fierce debate, a few strokes of genuine brilliance, and one of the greatest scientific revolutions of the 20th century, a revolution that most people have never even heard of, despite the fact that it completely changed how we understand the planet we live on. And it starts, as so many great scientific stories do, with someone that nobody believed. His name was Alfred Wegener, and he wasn't even a geologist. He was a German meteorologist and polar explorer, born in Berlin in 1880, and in 1912, he proposed an idea so radical, so seemingly absurd, that the geological establishment spent the next 50 years ridiculing him for it. The idea was this: the continents move. Not in some vague, metaphorical sense, literally, physically move. They drift across the surface of the Earth like massive, incredibly slow rafts, and hundreds of millions of years ago, they were all joined together in a single supercontinent, which Wegener called Pangaea, meaning all lands in Greek. Now, Wegener wasn't the first person to notice that the continents look like they might fit together. Look at a map of the Atlantic Ocean. The eastern coastline of South America and the western coastline of Africa match up almost perfectly, like two pieces of a jigsaw puzzle. People had been remarking on this since at least the 16th century, when the first decent maps of the Atlantic were drawn. But Wegener went much further than just the shapes. He compiled an enormous amount of evidence from multiple disciplines. He pointed out that identical fossils of ancient plants and animals were found on continents now separated by thousands of kilometers of open ocean. The same species of fern, Glossopteris, appeared in fossil beds in South America, Africa, India, Antarctica, and Australia. The same small freshwater reptile, Mesosaurus, was found in both Brazil and South Africa. These weren't animals that could have swum across the Atlantic. They weren't seeds that could have blown thousands of miles on the wind. The simplest explanation was that these land masses were once connected. He pointed to geological evidence too. Mountain ranges that seemed to continue from one continent to another. The Appalachian Mountains in eastern North America, for instance, line up almost perfectly with the Caledonian Mountains in Scotland and Scandinavia when you push the continents back together. Rock formations of the same age and type, sitting on opposite sides of oceans. Evidence of ancient glaciations in places that are now tropical, suggesting those lands were once much closer to the poles. The evidence was overwhelming, at least to Wegener, but the geologists hated it, and here's why. Wegener could describe what had happened. The continents had moved, but he couldn't explain how. He couldn't identify a mechanism powerful enough to shove entire continents across the face of the Earth. He suggested, somewhat vaguely, that maybe tidal forces or the rotation of the Earth could do it, But when physicists and geologists ran the numbers, those forces were nowhere near strong enough. Continents are enormous slabs of thick, heavy rock. The idea that they could somehow plow through the solid ocean floor seemed mechanically impossible. And so the establishment dismissed Wegener's theory. Not just dismissed it, actually. They were often quite nasty about it. A prominent American geologist called the theory utter damned rot. The president of the American Philosophical Society described it as the kind of thinking that takes considerable liberty with our globe. Wegener's continental drift hypothesis was treated by many serious scientists as the ravings of a dilettante who didn't understand proper geology. Wegener died in 1930, at the age of 50, on an expedition to Greenland. He was resupplying a remote weather station in the middle of the ice sheet, in temperatures around -50 degrees Celsius, and he died on the return journey, probably of a heart attack. His body was found the following spring, buried in the snow. He never saw his theory vindicated, and he wouldn't have, not for another 30 years. But here's where the story gets really interesting, and it connects directly to why volcanoes exist where they do. Because in the decades after Wegener's death, new evidence started piling up. Evidence he never could have gathered, because the technology didn't exist yet. And the crucial evidence came from the most inaccessible place on Earth, the bottom of the ocean. During and after World War II, the oceans got a lot more attention. Navies needed to understand underwater topography for submarine warfare. New sonar technology allowed scientists to map the ocean floor in detail for the first time. And what they found was astonishing. The ocean floor wasn't flat. It wasn't a featureless plain of sediment, the way most people had assumed. It had mountain ranges, enormous ones. Running through the middle of the Atlantic Ocean, roughly equidistant from the coastlines on either side, was a massive underwater mountain chain, the Mid-Atlantic Ridge, stretching from the Arctic to the Antarctic, one of the longest geological features on the planet. And similar ridges were found in every ocean. Now, one of the people who did the most to reveal this hidden landscape was a woman named Marie Tharp, and her story is one of those infuriating tales of brilliance being overlooked because of the era she lived in. Tharp was born in Michigan in 1920, studied geology and mathematics, and went to work at Columbia University's geology department in the late 1940s. But because she was a woman, she wasn't allowed to go on research cruises. She was confined to the lab. So while her male colleagues, including her longtime collaborator Bruce Heezen, went to sea and gathered sonar data, Tharp was the one who actually plotted it, who turned thousands of depth soundings into detailed maps of the ocean floor. And in doing so, she noticed something remarkable. Running along the crest of the Mid-Atlantic Ridge, she found a deep valley, a rift valley, like a crack running along the spine of the underwater mountain range. She recognized it for what it was, a rift zone, a place where the Earth's crust was being pulled apart. When she pointed this out to Heezen, he initially dismissed it. He said it sounded like girl talk. That's an actual quote, by the way. He later came around, but that initial reaction tells you everything about what women in science were up against in the 1950s. Tharp was right. The Rift Valley was a crucial piece of evidence that the ocean floor was splitting apart, that new material was welling up from below. And then came the clincher. In the 1960s, scientists studying the magnetic properties of rocks on the ocean floor discovered something extraordinary. The Earth's magnetic field, as it turns out, flips direction every few 100,000 years or so. North becomes south, south becomes north, and then it flips back. When new rock forms on the ocean floor, tiny magnetic minerals in the rock align themselves with whatever direction the magnetic field is pointing at the time. And when the rock solidifies, that alignment is locked in, like a compass needle frozen in stone. And when researchers mapped these magnetic patterns on either side of the mid-ocean ridges, they found perfect symmetry. Stripes of normal and reversed magnetic rock, mirroring each other on both sides of the ridge, like a barcode printed in duplicate. This was devastating evidence. It meant that new ocean floor was being created right at the ridge, pushed apart in both directions, and that the pattern recorded the history of the Earth's magnetic field as the floor spread. Harry Hess, a Princeton geologist who had actually commanded a naval vessel in the Pacific during the war and had used its sonar to map the ocean floor in his spare time between battles, proposed the mechanism that Wegener had been missing. He called it seafloor spreading. New material rises from the Earth's interior at the mid-ocean ridges, solidifies, and pushes the older material outward on both sides. The continents aren't plowing through the ocean floor. They're riding on top of moving plates, being carried along like packages on a conveyor belt. And what drives the conveyor belt? Heat. Convection currents in the Earth's mantle, enormous, slow-moving circulation patterns driven by the heat of the planet's interior, the same heat that makes those South African gold mines so unbearably hot. By the late 1960s, all of this evidence, the fit of the continents, the fossil distributions, the matching geological formations, the mid-ocean ridges, the magnetic symmetry, the seafloor spreading, all of it was synthesized into a unified theory: plate tectonics. The Earth's outer shell, the lithosphere, is broken into about 15 major plates and several smaller ones. These plates are rigid, relatively thin slabs of rock, ranging from about 5 kilometers thick under the oceans to over 200 kilometers thick under the continents. And they move, slowly, about as fast as your fingernails grow, typically 2 to 10 centimeters per year. But over millions of years, that adds up. Over hundreds of millions of years, continents cross oceans, mountain ranges rise and erode away, entire ocean basins open and close. The face of the Earth is constantly, relentlessly rearranging itself. And here is where volcanoes come roaring into the picture. Because the places where these plates meet, the boundaries between them, are where most of the Earth's volcanic and seismic activity is concentrated. There are 3 types of plate boundaries, and each one creates volcanic activity in its own characteristic way, and understanding those differences is the key to understanding why volcanoes behave so differently from one place to another. The first type is a divergent boundary, where 2 plates are moving apart. The mid-ocean ridges are divergent boundaries. As the plates separate, hot material from the mantle rises to fill the gap, partially melts as it rises because the pressure drops, and that melt, that magma, erupts at the surface to form new oceanic crust. This is happening right now, along the Mid-Atlantic Ridge, along the East Pacific Rise, along every mid-ocean ridge on the planet. Most of this volcanic activity happens deep underwater, where nobody sees it, but it's actually the most volcanically productive process on Earth. The mid-ocean ridges produce more lava, create more new rock, than all the world's land volcanoes combined. And in a few places, the mid-ocean ridge pokes above the surface, and you get to see it happening in real time. The most famous example is Iceland, which sits right on top of the Mid-Atlantic Ridge, literally straddling the boundary between the North American plate and the Eurasian plate. The island is being slowly pulled apart, about 2 centimeters per year, and the gap is constantly being filled by new volcanic rock. That's why Iceland has so many volcanoes, so many hot springs, so much geothermal energy. The island exists because of the ridge. It's a piece of the mid-ocean ridge that's grown tall enough to break the surface. The second type of boundary, and the one that produces the most dramatic and dangerous volcanoes, is the convergent boundary, where 2 plates are pushing into each other. And what happens there depends on what kind of plates are colliding. If an oceanic plate meets a continental plate, the oceanic plate loses, because oceanic crust is denser and thinner. It gets forced downward beneath the continental plate, plunging into the mantle at an angle. This is subduction, and it's the process that was happening beneath Vesuvius when it destroyed Pompeii. It's the process that built the Andes. It's the process responsible for the volcanoes of the Pacific Northwest, for Mount Rainier and Mount St. Helens and Mount Hood. It's the process that created the Ring of Fire, that great horseshoe of volcanic and seismic activity that encircles the Pacific Ocean, home to roughly 75% of the world's active and dormant volcanoes. And here's what's really fascinating about subduction, and this is where the chemistry starts to get interesting. When the oceanic plate dives down into the mantle, it carries water with it, seawater that's been absorbed into the minerals of the oceanic crust, locked into the crystal structure of certain rocks and clay minerals over millions of years on the ocean floor. As the plate descends and the temperature and pressure increase, that water gets squeezed out. It's released from the minerals and rises into the hot mantle rock above the descending plate. And here's the key. Water dramatically lowers the melting point of rock. Mantle rock that would otherwise be too cool to melt at those particular pressures and temperatures becomes able to partially melt when water is added. It's similar to how adding salt to ice makes it melt at a lower temperature, though the chemistry is different. The point is, the water triggers melting. It creates magma, where magma wouldn't otherwise exist, and the magma created by subduction is different from the magma at mid-ocean ridges. It's more complex, more chemically evolved, richer in silica and dissolved gases, and that, as we'll discover, makes all the difference in the world when it comes to how a volcano erupts. Because the amount of silica in the magma and the amount of gas dissolved in it, those two factors are what determine whether a volcano oozes peaceful rivers of lava like the ones in Hawaii, or whether it explodes with the kind of cataclysmic violence that buries cities and changes the climate of the entire planet. So let's talk about that. Let's talk about magma. Magma is just molten rock. That's all it is. Rock that's been heated to the point where it becomes liquid, or partially liquid, because in reality, magma is usually a messy mixture of liquid rock, dissolved gases, and crystals that are either still forming or haven't fully melted yet. Think of it less like water and more like a thick, lumpy, incredibly hot stew. And the properties of that stew, how runny or thick it is, what gases are dissolved in it, what minerals are crystallizing out of it, those properties control everything about how a volcano behaves. The single most important variable is viscosity. That's just a fancy word for how thick or resistant to flow a liquid is. Water has low viscosity. It flows easily. Honey has higher viscosity. It's thick and sluggish. And magma viscosity varies enormously depending on its chemical composition, specifically the amount of silica in it. Silica is silicon dioxide, the same stuff that makes up quartz and glass, and it's the most abundant mineral component in most rocks. And here's what silica does in magma. Silica molecules tend to link up into long chains and networks, tangling together, creating a kind of molecular mesh that resists flow. The more silica in the magma, the more tangled the mesh, the more viscous the magma. It's a bit like the difference between pouring juice and trying to squeeze toothpaste. Same basic idea, liquid coming out of an opening, but the experience is completely different. Now, the Earth produces magma with a wide range of silica content, and geologists categorize them into a few main types. At the low end, around 45 to 52% silica, you've got basaltic magma. This is the most common type of magma on Earth. It's what erupts at mid-ocean ridges and at hotspot volcanoes like Hawaii. It's relatively low in silica, which means it has low viscosity. It flows easily. When basaltic magma erupts, it tends to pour out in rivers and sheets, spreading across the landscape in broad, relatively gentle flows. It can be spectacular to watch, and it can certainly destroy property, but it rarely kills people in large numbers because you can generally see it coming and walk away from it. The Hawaiian word for a smooth, ropey type of lava flow is pahoehoe, and for a rough, chunky type, it's a, and both of those terms have been adopted by geologists worldwide, which is a nice little piece of Hawaiian linguistic imperialism in the earth sciences. At the other end of the spectrum, around 65% silica and above, you've got rheolitic magma. This stuff is thick, stiff, gas-rich, and dangerous. It's the toothpaste. When rhyolitic magma tries to erupt, the high viscosity means gases can't escape easily. They're trapped in the thick, sticky melt, building pressure, the way bubbles build in a bottle of soda that you've shaken up. And when that pressure finally exceeds the strength of the rock plugging the vent, the result isn't a gentle flow, it's an explosion. Sometimes a catastrophic explosion. The most violent volcanic eruptions in history have almost all involved silica-rich, high-viscosity magmas. In between, around 52 to 65% silica, you've got andesitic magma, named after the Andes Mountains. This is the typical magma produced at subduction zones, and it can go either way, sometimes erupting relatively peacefully, sometimes explosively, depending on a host of factors. Many of the world's most famous and dangerous stratovolcanoes, the tall, steep, beautifully conical ones, Fuji, Vesuvius, Mount Rainier, Pinatubo, are built primarily from andesitic eruptions. And here's the thing about dissolved gases. When magma is deep underground, under enormous pressure, gases stay dissolved in the melt, the same way carbon dioxide stays dissolved in a sealed bottle of soda. The pressure keeps it in solution. But as magma rises toward the surface, the pressure drops. And just like when you unscrew the cap on that soda bottle, the gas starts coming out of solution. Bubbles form. And in a high-viscosity magma, those bubbles can't rise and escape easily. They get trapped. More and more bubbles form. The magma starts to foam, and the pressure inside that foaming mass keeps building and building until something gives. The main volcanic gas is water vapor, surprisingly enough. It makes up roughly 60 to 80% of the gas released in most eruptions. After that comes carbon dioxide, sulfur dioxide, hydrogen sulfide, and smaller amounts of other gases. But it's mostly steam. The Earth, when it erupts, is largely exhaling water. So now you have the basic framework. Low silica, low viscosity magma tends to produce gentle, effusive eruptions, lava flows, the kind of thing you see in Hawaii. High silica, high viscosity magma tends to produce explosive eruptions, ash columns, pyroclastic flows, the kind of thing that destroyed Pompeii. And the type of magma you get depends largely on the tectonic setting. Mid-ocean ridges and hotspots produce mostly basaltic magma. Subduction zones produce more silica-rich magma because of the complex process by which the descending plate, the water it carries, and the overlying mantle all interact and partially melt and mix. But here's where it gets even more interesting, because the journey of magma from its source deep in the earth to the surface isn't simple. It's not like turning on a faucet. Magma has to fight its way up through kilometers of solid rock, and along the way, it changes. It cools slightly, and as it cools, certain minerals crystallize out of the melt, forming solid crystals that settle or stay suspended. And here's the subtle part. When those crystals form, they tend to remove specific elements from the remaining liquid, elements like magnesium and iron, leaving the liquid enriched in silica. So the longer magma sits underground and slowly cools, the more silica-rich the remaining liquid becomes. This process is called fractional crystallization, and it means that magma can evolve. It can start out as a relatively low silica basalt and, through slow cooling and crystal removal, become a higher silica, more viscous, more explosive composition. The magma essentially ages, and as it ages, it becomes more dangerous. Magma also collects in chambers underground, pockets and reservoirs within the crust, where it pools and waits, sometimes for centuries or millennia, before an eruption finally occurs. We used to think of magma chambers as big underground lakes of liquid rock, neat and self-contained. The reality turns out to be messier and more interesting. Modern geophysical imaging suggests that many magma storage zones are more like networks of partially molten mush, crystal-rich zones with liquid distributed between the crystals, more like a wet sponge than a bathtub. Only a fraction of the material may be truly liquid at any given time, but fresh injections of hot magma from deeper sources can remobilize this mush, reheating it, adding gas, adding pressure, and potentially triggering an eruption. Many major eruptions are thought to have been triggered not by a slow buildup of magma over time, but by a sudden injection of fresh, hot magma into an existing storage zone, like dumping hot water into a pot that was already close to boiling. All right, so now we've got the pieces in place. We understand why the Earth has heat. We understand, at least in broad strokes, how plate tectonics creates the conditions for magma to form. We understand that magma composition controls eruption style, and we understand that the journey from source to surface is complex and dynamic. Now let's see what happens when things go seriously, spectacularly wrong. Because the history of volcanoes is also a history of catastrophe, of moments when the Earth reminded humans, in the most brutal possible terms, exactly how powerful it is. And the story I want to tell first is the one that, in many ways, marks the beginning of modern volcanology. The eruption that forced the scientific world to start taking volcanoes seriously as objects of study, not just as exotic curiosities. It happened on May 8, 1902, on a small Caribbean island called Martinique, and it killed approximately 30,000 people in about 2 minutes. The volcano was called Mount Pelée. It's a stratovolcano in the northern part of Martinique, a French island in the Lesser Antilles, and the city that sat at its base was Saint-Pierre, the largest city on the island, the cultural and commercial capital, sometimes called the Paris of the Caribbean. About 30,000 people lived there. The harbor was full of ships. The streets were lively and cosmopolitan, and in April of 1902, the mountain started to wake up. The signs were unmistakable, in hindsight. Increased fumarole activity, venting of steam and gases from cracks near the summit, the smell of sulfur drifting down into the city. A crater lake near the top started to heat up and overflow. Small earthquakes rattled windows. Ash began to fall. A river of boiling mud came roaring down one of the valleys on the mountain's slope, destroying a sugar mill and killing about 23 people. Snakes, driven from their usual habitat on the upper slopes by the volcanic gases, descended into the city. Hundreds of pit vipers came slithering into the streets and houses, biting people and livestock. About 50 people and 200 animals were reportedly killed by the snakes alone, which is one of those details that's so bizarre it almost sounds made up, but it's well documented. And yet, the city didn't evacuate. There were political reasons for this, tragically. An election was scheduled for May 11th, just a few days away, and the governor wanted people to stay in Saint-Pierre so they could vote. The newspaper published reassuring articles. A scientific commission was dispatched to evaluate the danger, and concluded, incorrectly, that Saint-Pierre was safe. The governor himself came to Saint-Pierre and brought his family, as a show of confidence. It was a catastrophic misjudgment. On the morning of May 8, 1902, Pelée erupted. But it wasn't a simple explosion upward. What happened was something that, at the time, scientists had never really documented or understood. A superheated cloud of gas and volcanic debris, a pyroclastic flow, blasted out from the side of the mountain, not up, sideways. It rolled down the slope at tremendous speed. Some estimates say over 150 kilometers per hour, maybe much faster, and it was incredibly hot, somewhere around 1,000 degrees Celsius. It hit Saint-Pierre like a hurricane made of fire. It arrived so fast that people had no time to react, no time to run, no time to do anything at all. The city was obliterated. Every building was destroyed or gutted. Ships in the harbor were capsized and set ablaze. Of the roughly 30,000 people in Saint-Pierre that morning, the commonly cited number of survivors is 2. Just 2. One of them was a man named Louis Auguste Siparis, a prisoner who had been locked in a tiny, partially underground stone cell the night before for getting into a drunken brawl. The thick stone walls and the semi-buried position of his cell shielded him from the worst of the blast, though he was still horribly burned. He was rescued 4 days later and went on to tour with the Barnum and Bailey Circus as a sideshow attraction, billed as the man who survived the eruption of Mont Pelée, showing audiences the scars on his body. It's a strange and somewhat grim coda to a terrible tragedy. The destruction of Saint-Pierre shocked the world. It was front-page news everywhere. Scientists rushed to Martinique to study what had happened, and what they found there changed the science of volcanoes forever. Because the type of eruption that destroyed Saint-Pierre, the lateral blast, the devastating pyroclastic flow, was something the scientific literature had barely acknowledged. Most volcanic studies up to that point had focused on lava flows and vertical eruptions, the kind of thing people could observe from a relatively safe distance. The idea that a volcano could unleash a horizontal blast of superheated gas and debris, moving at hurricane speed, was a revelation. It was terrifying, and it was new. The French geologist Alfred Lacroix, who arrived in Martinique shortly after the eruption, coined a term for this type of pyroclastic flow. He called it a nuée ardente, a glowing cloud. The term captured the eerie appearance witnesses from a distance had described, a roiling, incandescent cloud that seemed to flow down the mountainside like a liquid, hugging the terrain, glowing from within. And the recognition of nuées ardentes as a distinct and deadly volcanic phenomenon was one of the most important advances in volcanology of the 20th century. It changed how scientists assessed volcanic hazards. It changed how they thought about the risks to people living near volcanoes. And it set the stage for understanding another lateral blast, a much more thoroughly studied one, that would happen on a different continent, 78 years later, at a mountain in the American Pacific Northwest that had been quiet for over a century. Mount St. Helens. If you were alive in 1980 and old enough to remember the news, you probably remember this one. And even if you weren't, you've probably seen the photographs, because the eruption of Mount St. Helens on May 18, 1980, is one of the most documented natural disasters in history. It happened in a developed country with good media infrastructure, and scientists had been watching the mountain for months, which means there's an extraordinary amount of data, photography, and testimony about what happened before, during, and after the blast. It's a story of brilliant science, stubborn defiance, heartbreaking loss, and one of the most dramatic demonstrations of geological power that anyone alive today has ever witnessed. Let's set the scene. Mount St. Helens is a stratovolcano in the Cascade Range in southwestern Washington state, about 80 kilometers northeast of Portland, Oregon. Before the eruption, it was considered one of the most beautiful mountains in the Cascades, a nearly perfect snow-capped cone, sometimes called the Mount Fuji of America. It rises in the middle of dense old-growth forests, near rivers and lakes. Hikers loved it. It was a popular recreation area. And geologists knew it was dangerous. In fact, just 2 years before the eruption, in 1978, two USCA's geologists named Dwight Crandell and Donal Mullineaux published a report warning that Mount St. Helens was the most likely volcano in the Cascades to erupt in the near future, possibly before the end of the century. They based this on the geological record, on studies of the mountain's past eruptions, which showed that St. Helens was by far the most frequently active volcano in the range. It had erupted repeatedly over the past 4,000 years, most recently in the mid-1800s. Their report was prescient, almost eerily so. But even they didn't predict exactly what would happen. On March 20th, 1980, a magnitude 4.2 earthquake struck beneath the mountain. Then more earthquakes, hundreds of them, then thousands. By late March, the mountain had started venting steam and ash from its summit. A new crater was forming. And something else was happening, something that would turn out to be crucial. The entire north face of the mountain was bulging outward. A massive cryptodome, a body of magma that had pushed up into the mountain but hadn't broken through the surface, was inflating the north flank like a blister. By early May, the bulge had grown by about 150 meters. The north face was literally being pushed outward at a rate of about 1.5 to 2 meters per day. Geologists watched this with increasing alarm. They knew the bulge was unstable. They knew it could collapse. But the timing, as always with volcanoes, was impossible to predict with precision. One of the scientists monitoring the mountain most closely was David Johnston, a USC's volcanologist. Johnston was 30 years old, passionate, dedicated, and deeply concerned about the danger the mountain posed. He had been studying the gases coming from the volcano and had concluded that a major explosive eruption was likely, not just a minor steam event. He advocated strongly for keeping people away from the mountain, but he also took shifts at the closest observation post, Coldwater 2, on a ridge about 9 kilometers from the summit. He was there on the morning of May 18th, and here we need to talk about Harry Truman, and I don't mean the president. Harry R. Truman was an 83-year-old innkeeper who ran the Mount St. Helens Lodge on Spirit Lake, right at the base of the mountain. He'd lived there for over 50 years. He loved the mountain. He loved his lodge, his cats, his boat, his life on the lake. And when authorities established a restricted zone around the volcano and told people to evacuate, Harry refused to leave. Flatly, colorfully, stubbornly refused. He told reporters, and there were many, because he became a minor celebrity during the buildup, that the mountain wouldn't hurt him, that he'd been there his whole adult life and it had never done anything, that he'd rather die than leave. He said the scientists were overreacting. He was wrong, and on the morning of May 18th, at 8:32 a.m. Pacific Daylight Time, the mountain proved just how wrong. Here's what happened, as precisely as the evidence allows us to reconstruct it. A magnitude 5.1 earthquake struck directly beneath the volcano. The shaking destabilized the already precarious north face, the bulge that had been growing for weeks, and the entire north flank of the mountain collapsed in a colossal landslide. This was the largest landslide in recorded history, roughly 2.5 cubic kilometers of rock and ice and debris sliding northward off the face of the mountain at speeds of 175 to 250 kilometers per hour. And the moment that massive plug of rock moved, it was like uncorking a bottle. The magma and superheated water and gases that had been building pressure behind the bulge were suddenly released. The result was a lateral blast, a directed explosion northward that overtook and then outran the landslide itself. The blast cloud was a mixture of superheated gas, pulverized rock, volcanic ash, and ice fragments. traveling at speeds that may have reached 480 to over 1,000 kilometers per hour in the first few seconds. Some estimates put the initial velocity as high as Mach 1, the speed of sound. The temperature within the blast was roughly 300 degrees Celsius, though some areas near the vent may have been much hotter. The blast leveled old-growth forests like matchsticks. Trees that had stood for centuries, massive Douglas firs a meter or more in diameter, were snapped off at their bases or ripped from the ground entirely and hurled through the air. The devastation zone extended roughly 30 kilometers from the volcano. In the innermost zone, the trees were simply vaporized or carried away. Farther out, they were laid flat, all pointing in the same direction away from the blast, like a vast field of felled toothpicks. David Johnston was at Coldwater 2 when the blast hit. He had just enough time to radio in a single, now famous transmission. "Vancouver, Vancouver, this is it." Then his signal cut off. His body was never found. The blast swept over his position at a speed that left no time for escape. 57 people died in the eruption, including Harry Truman, whose lodge and Spirit Lake were buried under the landslide debris, hundreds of feet deep. The beautiful conical summit of the mountain was gone, replaced by a gaping, horseshoe-shaped crater blown open to the north. The mountain lost about 400 meters of elevation. Its profile was transformed forever, and the eruption didn't stop with the lateral blast. With the north face removed, a vertical eruption column punched up through the open crater, shooting ash and pumice into the stratosphere, reaching an altitude of about 25 kilometers within 15 minutes. The eruption column rained ash over eastern Washington and beyond. The city of Yakima, about 130 kilometers to the east, was plunged into near-total darkness in the middle of the day as ash fell so thickly that streetlights came on automatically. Ash from the eruption was detectable in the atmosphere for weeks and circled the globe. Meanwhile, the massive landslide had filled the entire upper North Fork Toutle River Valley with debris, and when volcanic heat mixed with snow and ice, enormous mud flows, called lahars, roared down the river valleys, destroying bridges, roads, logging camps, and houses for dozens of kilometers downstream. The eruption of Mount St. Helens was, by global volcanic standards, a moderate event. It was a VEI 5 on the Volcanic Explosivity Index, which goes from 0 to 8. The eruption that destroyed Pompeii was also about a VEI 5. There have been eruptions in human history that were vastly more powerful, but St. Helens was transformative for volcanology because it was so thoroughly studied, before, during, and after. Scientists had monitoring equipment in place. They had data from the pre-eruption buildup. They had seismic recordings, gas measurements, tilt meters tracking the bulge. Photographers and filmmakers, some of whom died in the blast, captured images of the collapse and explosion in real time. The eruption became one of the most analyzed geological events in history, and the lessons learned at St. Helens reshaped volcanic hazard assessment around the world. One of the most important lessons was about lateral blasts. Before St. Helens, the hazard models for most volcanoes assumed that the primary danger zone was directly above and immediately around the summit. Pyroclastic flows were understood to travel down valleys and drainages, pulled by gravity. But St. Helens showed that the initial blast could be directed sideways, across ridges and valleys, covering a much wider and more unexpected area than any gravity-driven flow would reach. David Johnston's observation post on a ridge 9 kilometers from the summit was considered relatively safe under the prevailing models. It wasn't. The blast went over the ridge as easily as water over a rock. That lesson has changed how volcanologists define hazard zones ever since. Another lesson was about the scale and speed of volcanic landslides and the complex chain of events they can trigger. The St. Helens eruption wasn't a single phenomenon. It was a cascading sequence: earthquake, landslide, lateral blast, vertical eruption, pyroclastic flows, lahars, ash fall. Each one triggered or amplified the next. Modern volcanic hazard assessments now try to account for these cascading interactions, which is enormously complex but essential. And then there's the ecological aftermath, which turned out to be as fascinating as the eruption itself. In the immediate aftermath, the blast zone looked like the surface of the moon, hundreds of square kilometers of forest, completely leveled or buried. Streams choked with debris. Spirit Lake filled with floating logs and volcanic sediment, its temperature soaring. Scientists expected recovery to take centuries, and some of it will. But what actually happened in the years after the eruption surprised almost everyone. Life came back, and it came back faster and in more interesting ways than anyone had predicted. Fireweed and lupine sprouted in the ash within a year. Pocket gophers that had survived underground in their burrows churned up buried soil, mixing it with the ash and creating pockets of nutrients. Elk returned within a few years. Birds brought seeds. And the process of ecological succession, the slow rebuilding of a biological community from scratch, became one of the most studied examples in the world. Mount St. Helens became, paradoxically, one of the most important laboratories for understanding how life recovers from catastrophe. There's a detail about the aftermath that's worth pausing on. The lateral blast at St. Helens carved the landscape into distinct zones that scientists later mapped with care. Closest to the volcano was the direct blast zone, where everything was scoured down to bare rock. Then came the channelized blast zone, where the blast followed topographic channels and valleys. And beyond that was the singe zone, where standing trees were left upright, but killed by the heat of the blast cloud. Their needles turned brown in an instant. The boundary between the blowdown zone, where trees were flattened, and the standing dead zone, where they remained upright but scorched, was sometimes remarkably sharp. On one side of a ridge, complete devastation, trees laid flat. On the other side, trees standing but dead. The physics of the blast, the way it interacted with the terrain, created a mosaic of destruction that scientists would study for decades. And then there was Spirit Lake. Before the eruption, Spirit Lake was a pristine alpine lake at the north base of the mountain, surrounded by old-growth forest. Harry Truman's lodge sat on its shore. The landslide buried the entire north end of the lake and pushed a massive wave across it, stripping the surrounding hillsides of their forest. The lake was left clogged with millions of logs, covered with a thick mat of floating debris and volcanic sediment. Its temperature soared. Scientists initially worried that Spirit Lake was biologically dead, but within a few years, bacteria and algae began to colonize the lake. Amphibians returned, insects appeared. The floating log mat slowly waterlogged and sank. The lake, like the forest around it, began the long process of recovery, demonstrating yet again that life is astonishingly tenacious, even in the face of catastrophic disruption. But while St. Helens taught the world about lateral blasts and ecological resilience, another eruption was brewing on the other side of the Pacific, one that would teach an equally important but very different lesson, a lesson about the power of scientific prediction and the human and political challenges of acting on that prediction in time. And this eruption, when it came, would be one of the largest of the 20th century, and its successful prediction would save tens of thousands of lives, but at a cost that nobody fully anticipated. The volcano was Mount Pinatubo in the Philippines, on the island of Luzon, and before 1991, almost nobody paid it much attention. It wasn't on most lists of particularly dangerous volcanoes. It hadn't erupted in living memory, and in fact, there was no clear historical record of any eruption from Pinatubo at all. The mountain was heavily forested, its summit overgrown, and indigenous Ayeta people lived on its slopes. The nearby Clark Air Base, a massive U.S. military installation, had been built right next to the volcano, and the tens of thousands of American and Filipino military personnel and their families who lived and worked there didn't give the mountain much thought. It was just a mountain. Sound familiar? In mid-1990, that changed. On July 16, 1990, a major earthquake struck the island of Luzon. The magnitude 7.7 Luzon earthquake, one of the deadliest in Philippine history. Its epicenter was about 100 kilometers northeast of Pinatubo, and while the earthquake itself wasn't volcanic, it appears to have disturbed the plumbing beneath Pinatubo, destabilizing the magma system that had been sitting quietly for centuries. Within weeks, small steam explosions began venting from the volcano's upper slopes. Locals reported increased hot spring activity. The mountain was waking up. Philippine and American scientists mobilized. The Philippine Institute of Volcanology and Seismology, PHIVOLCS, set up monitoring stations. The USCIS sent a team of volcanologists from their newly formed Volcano Crisis Assistance Team, a group specifically created to help monitor developing volcanic crises around the world. And among the scientists who arrived was a USCIS volcanologist named Chris Newhall, who had been studying Philippine volcanoes and who quickly recognized that Pinatubo's geological record, once he and his colleagues started digging into it, was terrifying. Here's what they found. Pinatubo had erupted before, and on a massive scale. Geological fieldwork revealed deposits from previous eruptions that were enormous, suggesting that the volcano was capable of eruptions far larger than anything the region had planned for. The last major eruption appeared to have been roughly 500 years ago, possibly around 1500 CE, though the record was uncertain. The deposits showed that pyroclastic flows from past eruptions had traveled many kilometers down every drainage radiating from the summit. Whatever was building inside Pinatubo, it had the potential to be very, very big. Through the first half of 1991, the signs kept escalating. Seismic activity increased steadily. The earthquake count rose from a few per day to hundreds. Sulfur dioxide gas emissions spiked dramatically, reaching about 5,000 tons per day by late May, a strong indicator of fresh magma rising toward the surface. Small phreatic eruptions, steam-driven explosions caused by groundwater being heated by the approaching magma, began in early April. The scientists watched the data and made a call that took extraordinary courage. They told the Philippine government and the American military to evacuate. This was not a popular recommendation. Clark Air Base was a strategically important installation. Evacuating it would be enormously expensive and disruptive. The surrounding communities, home to hundreds of thousands of people, would be difficult to move. And volcanic predictions are inherently uncertain. The scientists couldn't say exactly when the eruption would happen, or exactly how big it would be. They could only say that a very large eruption was likely, probably within weeks, and that the danger zones extended far beyond what most people assumed. The scientists produced a series of alert levels, modeled partly on the system developed after Mount St. Helens, and crucially, they produced a simple, compelling hazard map showing the likely extent of pyroclastic flows and lahars. They also did something brilliant and perhaps unprecedented in volcanology at that time. They put together a short video explaining the dangers of pyroclastic flows and volcanic mud flows, using footage from past eruptions. They showed this video to local officials, military commanders, community leaders, and residents. Seeing actual footage of pyroclastic flows, seeing the sheer speed and destructiveness of them, was far more persuasive than any graph or technical briefing. It convinced people in a way that numbers alone could not. In the days leading up to the eruption, tens of thousands of people were evacuated. The Eta communities on the upper slopes were moved. Residents of the surrounding lowlands were relocated. Clark Air Base was evacuated in stages, with the final evacuation of about 14,000 personnel completing just days before the climax. And on June 15, 1991, Pinatubo erupted. Massively. The eruption was a VEI-6, the second largest eruption of the 20th century, after Nova Rupta in Alaska in 1912. The eruption column rose to about 40 kilometers, well into the stratosphere. Pyroclastic flows raced down every drainage from the summit, reaching distances of 12 to 16 kilometers, burying entire river valleys under deposits that were, in places, 200 meters thick. The volume of material ejected was roughly 10 cubic kilometers. And to make everything worse, a typhoon, Typhoon Yunya, hit the island almost simultaneously, dumping torrential rain that mixed with the ash to create devastating lahars, volcanic mudflows that destroyed bridges and buried towns under meters of heavy, wet sediment. The weight of the wet ash collapsed roofs across the region. Despite the enormous scale of the eruption, the prediction and evacuation effort saved an estimated 5,000 to 20,000 lives. That's the consensus among volcanologists. If no evacuation had occurred, the death toll would have been catastrophic, rivaling or exceeding Pelée. As it was, the eruption killed about 800 people, most of them from roof collapses under the weight of rain-soaked ash and from lahars in areas that were difficult to fully evacuate. Every one of those deaths was a tragedy. But the prediction was, by any measure, one of the great success stories of modern Earth science. It demonstrated that volcanic eruptions, while not predictable with clockwork precision, can be anticipated well enough to save enormous numbers of lives, if the science is good, if the communication is clear, and if the political will to act exists. Pinatubo had one more surprise, though, and this one was global. The eruption injected roughly 20 million tons of sulfur dioxide into the stratosphere, the highest injection measured up to that time. That sulfur dioxide reacted with water vapor to form a layer of sulfuric acid aerosol droplets that spread around the entire planet within weeks. And those tiny droplets reflected sunlight back into space, cooling the Earth's surface. Global average temperatures dropped by about 0.5 degrees Celsius for a year or two after the eruption. The effect was measurable, unmistakable. Pinatubo temporarily offset the warming trend from greenhouse gas emissions for about 2 to 3 years. Sunsets around the world were unusually vivid and colorful because of the stratospheric aerosols scattering light. It was a real-time demonstration, observed with modern instruments, of something that volcanoes have been doing throughout Earth's history, changing the climate. And one more detail about Pinatubo that I find remarkable. The eruption happened at the same time as Typhoon Yunya, and the combination was devastating. Imagine the scene. You've just experienced the second largest eruption of the century. Ash is falling from the sky, in quantities measured in meters, and simultaneously, you're being hit by a typhoon with torrential rain and high winds. The rain mixed with the ash to create a heavy, cement-like slurry that collapsed roofs across the region. Buildings that might have withstood the ash alone, or the rain alone, couldn't survive both. Many of the people who died at Pinatubo died not from pyroclastic flows, or even from ashfall directly, but from the roofs of their shelters caving in under the weight of wet ash. It's a sobering reminder that volcanic hazards don't exist in isolation. They interact with weather, with earthquakes, with the specific circumstances of the moment, in ways that can compound the danger in unexpected ways. And that's a thread worth pulling on, because the climate effects of volcanic eruptions are one of the most fascinating intersections of geology and atmospheric science, and the single most dramatic example in recorded history happened not at Pinatubo, but at a different Indonesian volcano, 76 years earlier, in April of 1815, and the eruption was so powerful, and its aftermath so devastating, that the following year became known as the Year Without a Summer. The volcano was Tambora, on the island of Sumbawa, in what is now Indonesia. Before 1815, Tambora was one of the tallest mountains in the Indonesian archipelago, standing about 4,300 meters high. The eruption, which began in earnest on April 10, 1815, was the most powerful eruption in at least 1,300 years, rated VEI 7 on the Volcanic Explosivity Index. That's 10 times more powerful than Pinatubo, 100 times more powerful than Mount St. Helens. The eruption column reached the stratosphere. Pyroclastic flows swept across the island and into the surrounding sea, creating steam explosions where the superheated material hit the water. The noise of the eruption was heard over 2,600 kilometers away. People on distant islands thought they were hearing cannon fire and sent military expeditions to investigate. Tambora ejected roughly 160 cubic kilometers of material. To put that in perspective, Mount St. Helens ejected about 1 cubic kilometer. The top 1,400 meters of the mountain were simply gone, replaced by a caldera 6 kilometers across and more than a kilometer deep. On the island of Sumbawa and neighboring Lombok, the immediate death toll was at least 10,000 from the eruption itself, from pyroclastic flows and fallout. But tens of thousands more died in the following months, from famine and disease, as crops were destroyed, water was contaminated, and the region was buried under volcanic debris. But the global effects were what made Tambora truly extraordinary. The massive injection of sulfur dioxide into the stratosphere created a worldwide aerosol veil that reduced incoming solar radiation. In 1816, the following year, temperatures across the northern hemisphere dropped significantly. Europe and North America experienced one of the coldest summers on record. Frost in June and July, snow in August, in places like New England and the Canadian Maritimes, crop failures across Europe, which was already economically devastated by the Napoleonic Wars, led to widespread famine, social unrest, and disease outbreaks. Grain prices spiked. Tens of thousands of people starved or died from typhus and other diseases linked to malnutrition and displacement. And here's one of those wonderful, tangential connections that makes history feel woven together. In the summer of 1816, a group of friends rented a villa on the shores of Lake Geneva in Switzerland. The weather was miserable, cold and rainy, dark and gloomy, the volcanic aerosols having ruined what should have been a pleasant summer. Stuck indoors, the friends challenged each other to write ghost stories. The group included Percy Bysshe Shelley, the poet, and his 18-year-old companion, soon to be his wife, Mary Wollstonecraft Godwin. And that summer, in that gloom and cold brought on by a volcanic eruption half a world away, the young Mary Shelley began writing a novel about a scientist who creates a living being from dead matter. The novel was Frankenstein. You could argue, and some literary scholars have, that one of the most influential works of science fiction ever written was, in a roundabout way, a consequence of the eruption of Mount Tambora. The volcano changed the weather changed the summer plans, and the ruined summer sparked a masterpiece. But Tambora isn't even the biggest eruption we know about, not by a long shot. And this is where the story takes us into territory that's both scientifically fascinating and, honestly, a little bit terrifying. Because the Earth is capable of eruptions so large that they make Tambora look like a firecracker. Eruptions that can reshape continents, alter the global climate for decades, and potentially threaten the survival of entire species including our own. And the evidence for these eruptions is written in the rocks, in the ice cores, and in our own DNA. Let me tell you about supervolcanoes. Now, supervolcano isn't a formal geological term. You won't find it defined precisely in most volcanology textbooks, but it's entered the language, and scientists use it informally to refer to volcanic systems capable of producing eruptions, with a volcanic explosivity index of 8, the highest level on the scale. A VEI 8 eruption ejects more than 1,000 cubic kilometers of material. For comparison, Mount St. Helens was about 1 cubic kilometer, Pinatubo was about 10, Tambora was about 160. A VEI 8 eruption is at least 1,000. It's an almost incomprehensible scale of violence, and they've happened multiple times. The geological record is clear on this. About 74,000 years ago, a volcano called Toba erupted on the island of Sumatra in Indonesia. It was a VEI 8, one of the largest eruptions in the last 2 million years. The eruption produced about 2,800 cubic kilometers of material, roughly 17 times more than Tambora. The caldera it left behind is now Lake Toba, about 100 kilometers long and 30 kilometers wide. It's the largest volcanic lake in the world. You can see it on a map. It's enormous. The climatic effects of the Toba eruption are still debated, but some scientists have proposed what's called the Toba catastrophe theory. The idea is that the eruption caused a severe global volcanic winter, with temperatures dropping by as much as 3 to 5 degrees Celsius globally, and perhaps much more in some regions, lasting years to decades. Sulfuric acid aerosols in the stratosphere would have blocked sunlight. Ash would have blanketed enormous areas, destroying vegetation. And here's the really provocative part. Some genetic studies suggest that around the time of Toba, the human population may have crashed dramatically, possibly to as few as a few thousand, or perhaps 10 to 15,000 breeding individuals. This is inferred from the surprisingly low genetic diversity in modern humans compared to other great apes. We are, genetically speaking, a remarkably homogeneous species, and one possible explanation is that we went through a severe population bottleneck around 74,000 years ago, right around the time of Toba. Now, I should say that the Toba catastrophe theory is controversial. Some scientists argue that the genetic bottleneck may have had other causes, or that the climatic effects of Toba, while severe, weren't as devastating as initially proposed. More recent ice core and sediment studies suggest the global cooling may have been less extreme than the earlier estimates, and archaeological evidence from Africa and India shows that some human populations seem to have survived through the Toba period without obvious disruption. So the picture is complicated. But the basic point stands. The Earth is capable of eruptions that can genuinely threaten the viability of entire species, and Homo sapiens may have come uncomfortably close to the edge. And here's the thing that makes this more than just ancient history. There are supervolcanic systems that are active today, right now. And the most famous one is sitting right in the middle of the United States, under one of the most beloved national parks in the country, Yellowstone. Yellowstone National Park, in the northwest corner of Wyoming, is famous for its geysers, its hot springs, its mud pots, its wildlife. Millions of people visit every year. Old Faithful erupts on schedule. Tourists take photographs. Bears wander through meadows. It's beautiful and serene, and the whole thing is sitting on top of an enormous magma system that has produced 3 supereruptions in the past 2.1 million years. The first was about 2.1 million years ago, the Huckleberry Ridge eruption, which produced about 2,500 cubic kilometers of material. The second was about 1.3 million years ago, the Mesa Falls eruption, smaller but still massive, at about 280 cubic kilometers. And the third was about 640,000 years ago, the Lava Creek eruption, producing about 1,000 cubic kilometers. The caldera from that last eruption is what forms the broad, flat valley that contains much of the park today. It's roughly 72 by 55 kilometers across. Most visitors don't even realize they're standing inside a caldera because it's so big that the rim just looks like distant mountains. Now, let me be clear about something, because this topic tends to generate sensational headlines and needless anxiety, and that's not what we're here for tonight. The probability of a Yellowstone supereruption happening in any given year is extraordinarily low. The USGS estimates it at roughly 1 in 730,000, something like that. The intervals between the past eruptions aren't regular enough to support the idea that one is overdue, despite what you might see in breathless documentaries. The volcano is intensely monitored, with seismometers, GPS stations, satellite radar, gas sensors, and thermal imaging all keeping continuous watch. If magma were starting to move toward the surface in a way that suggested an imminent eruption, we'd almost certainly see it coming, probably years to decades in advance. This is not something to lose sleep over. Literally, you're supposed to be falling asleep right now. But the science of what's happening beneath Yellowstone is genuinely fascinating, even without the apocalyptic framing. The heat source for Yellowstone's volcanism is a mantle plume, a column of unusually hot material rising from deep in the Earth's mantle, possibly from near the core mantle boundary, about 2,900 kilometers down. This plume is essentially stationary relative to the moving North American plate above it. As the plate drifts slowly to the southwest, the plume's hotspot stays in place, burning through the overlying crust in different locations over time. If you trace the path of the hotspot backward through time, following the trail of progressively older calderas and volcanic deposits, it runs northeast across the Snake River Plain of southern Idaho, marking the track of the North American plate's passage over the plume over the past 16 million years or so. Yellowstone is just the current location where the plume intersects the surface. And this brings us back to a concept we talked about earlier when we discussed the Hawaiian Islands and the goddess Pele. Hawaii, like Yellowstone, is a hotspot volcano. The Hawaiian chain formed as the Pacific plate moved over a deep mantle plume, creating a string of volcanic islands, each one active only while it sat over the plume, then going dormant as the plate carried it away. The Big Island, with its active volcanoes Kilauea and Mauna Loa, is the current position. The older islands to the northwest are extinct, and beyond the visible islands, the chain continues as a string of submerged seamounts stretching all the way to the Aleutian Trench, recording over 80 million years of plate motion. Now, Hawaiian volcanism is about as different from Yellowstone volcanism as you can get, even though both are driven by mantle plumes. And the difference comes back to that critical variable we talked about, magma composition. The Hawaiian plume rises through oceanic crust, which is thin and basaltic. The magma it produces is also basaltic, low in silica, low in viscosity. It erupts gently, in flows that tourists can, with appropriate caution, sometimes walk right up to. Kilauea has been erupting nearly continuously for decades, producing vast fields of pahoehoe and a'a lava that have extended the island's coastline by hundreds of acres. It's destructive, certainly. It has overrun roads and neighborhoods, and even buried entire subdivisions. But it's rarely explosive. People generally have time to evacuate. Yellowstone's plume, by contrast, rises through thick continental crust, which is rich in silica. The magma that forms in this setting, especially after it's had time to sit and evolve in crustal storage zones, tends to be rhyolitic, high in silica, high in viscosity, loaded with dissolved gases. It's the worst possible combination for explosive potential. And that's why Yellowstone's eruptions, when they happen, are so catastrophically violent, while Hawaii's are relatively gentle. Same basic process, a mantle plume delivering heat from the deep earth. Completely different results because of the crust that the plume has to punch through. Let me switch gears here for a moment, because we've been talking about the most dramatic, most violent volcanic events, the headliners, the ones that make the news and the documentaries. And those are important. But there's another kind of volcanic story that I think is equally fascinating and a lot less well known. And that's the story of how volcanic eruptions have shaped human civilization in subtler, more pervasive ways. Because here's something that might surprise you. For all the destruction they cause, volcanoes have been, on balance, one of the most beneficial geological forces for human life. And that paradox, that something so dangerous can also be so essential, is one of the most interesting things about them. Think about soil. If you've ever visited a volcanic region, you've probably noticed how green it is, how lush, how fertile. The area around Mount Etna in Sicily, the slopes of Vesuvius, the highlands of Central America, the islands of Indonesia, the Rift Valley of East Africa, Hawaii, the vineyards of Oregon's Willamette Valley, which sit on ancient volcanic soil. Some of the most productive agricultural land on Earth is volcanic, and that's not a coincidence. Volcanic rocks are rich in minerals, in potassium, phosphorus, calcium, magnesium, iron, all the elements that plants need to grow. When volcanic rock weathers, when it breaks down over time through exposure to rain and biological activity, those minerals are released into the soil. Volcanic ash, in particular, weathers rapidly because of its fine grain size and high surface area, enriching soil in a matter of years to decades, rather than the centuries or millennia it takes for harder rocks to break down. That's why civilizations have clustered around volcanoes throughout history, despite the danger. The soil is too good. The harvests are too rich. The risk is a price that millions of people have been willing to pay, generation after generation. And it's not just soil. Volcanoes have shaped human settlement, trade routes, culture, and architecture. The Romans built with volcanic tuff, a lightweight, easily carved rock formed from compacted volcanic ash. Roman concrete, one of the most durable building materials in history, the stuff that holds together the Pantheon and countless other structures that have lasted 2,000 years, was made using volcanic ash from the region around Pozzuoli, near Naples. The ash reacted with lime and seawater in a way that created an incredibly strong, waterproof cement. Modern engineers have studied Roman concrete to try to understand why it's lasted so long, and the key ingredient is the volcanic ash. It's called pozzolanic cement, named after Pozzuoli, and variants of it are still used today. Every time you see a structure made with Portland cement that has fly ash or volcanic aditite mixed in, you're looking at a descendant of Roman engineering that was, at its root, a gift from Vesuvius and its neighbors. Volcanic heat itself is a resource. Geothermal energy, the harvesting of heat from the Earth's interior, is a significant source of electricity and heating in volcanically active regions. Iceland gets about a quarter of its electricity and roughly 90% of its home heating from geothermal sources. The country is essentially powered by the same geological process that creates its volcanoes. Kenya, the Philippines, New Zealand, Indonesia, El Salvador, all use geothermal energy to some degree, and the potential is enormous. It's clean, it's reliable, it's not dependent on weather the way solar and wind are, and it's available anywhere that volcanic heat is close enough to the surface. There's something poetic about harnessing the same force that buries cities to heat homes and power hospitals. But perhaps the most profound and least appreciated gift of volcanoes is this: they are almost certainly one of the reasons life exists on Earth at all. And that claim might sound dramatic, but the evidence for it is strong, and it connects volcanoes to the biggest questions in all of science. Where did our atmosphere come from? Where did the oceans come from? How did the Earth become a planet that can support life? Here's the story. When the Earth first formed, about 4.5 billion years ago, it was a hellscape. A molten or semi-molten ball of rock, bombarded by asteroids and comets, with no atmosphere to speak of, and certainly no oceans. The early atmosphere, to the extent there was one, was probably stripped away by the intense solar wind from the young sun and by the violence of impacts. So where did our atmosphere come from? Where did all this air we're breathing come from? The answer, or at least a major part of the answer, is volcanoes, a process called volcanic outgassing. As the Earth's interior heated up and began to convect, as magma rose to the surface and erupted, it released gases, enormous quantities of gases, over hundreds of millions of years. Water vapor, carbon dioxide, nitrogen, sulfur compounds. These gases accumulated over time, building the Earth's second atmosphere, the one that eventually became the air we breathe. The early atmosphere was very different from today's. It was rich in carbon dioxide and had essentially no free oxygen. But it was an atmosphere, a blanket of gas that could trap heat, regulate temperature, and, critically, allow liquid water to exist on the surface. And liquid water, once it condensed, formed the oceans. The water in the oceans, every drop of it, was once inside the Earth, dissolved in magma, and was released to the surface through volcanic eruptions. When you look at the ocean, you're looking at the exhaled breath of 4 billion years of volcanism. Now, I should note that some of Earth's water may also have come from comets and asteroids, delivering water ice from the outer solar system. That's a real contribution, and its relative importance is still debated. But volcanic outgassing is almost certainly the dominant source. And beyond just providing the raw materials for atmosphere and ocean, volcanoes also played a crucial role in regulating the Earth's climate over geological timescales, keeping conditions stable enough for life to evolve and persist. Here's how that works. It's called the carbon silicate cycle, and it's one of the most beautiful feedback loops in all of Earth science. Volcanoes continuously emit carbon dioxide into the atmosphere. That CO2 creates a greenhouse effect, warming the planet. But carbon dioxide is also removed from the atmosphere by a process called silicate weathering. When rain falls on silicate rocks, the water, which is slightly acidic because it has dissolved some of the atmospheric CO2, reacts with the minerals in the rock. This chemical reaction consumes CO2 and converts it into dissolved bicarbonate ions, which are carried by rivers to the ocean, where they eventually end up in the shells of marine organisms and in sediment on the ocean floor, locking the carbon away. Now, here's the beautiful part. The rate of silicate weathering depends on temperature. When the planet is warmer, there's more evaporation, more rainfall, more weathering, more CO2 removed from the atmosphere, which cools the planet. When the planet is cooler, there's less rainfall, less weathering, less CO2 removal, and the continuing volcanic emissions cause CO2 to build up, warming the planet again. It's a thermostat, a natural, geological thermostat, operating over timescales of hundreds of thousands to millions of years, that has kept Earth's surface temperature within a range compatible with liquid water for most of the planet's history. Without volcanoes supplying the CO2, the thermostat wouldn't work. The Earth would eventually lose all its atmospheric carbon dioxide to weathering and become a frozen snowball, possibly permanently. Without the weathering to remove the CO2, the volcanic emissions would build up unchecked and turn Earth into a runaway greenhouse, like Venus, which has an atmosphere that's about 96% CO2 and a surface temperature of about 460 degrees Celsius, hot enough to melt lead. The balance between volcanic input and weathering removal is what has kept Earth in the sweet spot. Volcanoes, in a very real sense, are one of the reasons the planet is habitable. And speaking of other planets, this is maybe a good moment to mention that volcanoes aren't unique to Earth. They exist throughout the solar system, and some of them are spectacularly larger and stranger than anything on our planet. Mars has Olympus Mons, the largest known volcano in the solar system. It's a shield volcano, similar in type to the Hawaiian volcanoes, but on a scale that's almost hard to process. It's about 21.9 kilometers high, roughly 2.5 times the height of Mount Everest as measured from sea level, and its base is about 600 kilometers across, roughly the size of the state of Arizona. Its caldera at the summit is about 80 kilometers wide and contains multiple collapse craters nested inside each other. It's so wide and so gently sloped that if you were standing on its flank, you wouldn't be able to tell you were on a volcano. The curvature of Mars would hide the summit beyond the horizon. Why is Olympus Mons so much bigger than any volcano on Earth? Because Mars doesn't have plate tectonics. On Earth, the tectonic plates move over the hotspots, so the volcanic activity migrates, creating chains of islands or calderas. No single volcano sits over the hotspot long enough to grow truly enormous. But on Mars, with no plate motion, the Hawaiian-style plume just stays in one spot and keeps building the same volcano, layer after layer, eruption after eruption, for hundreds of millions of years. The result is a volcano the size of a small country. Venus has more volcanoes than any other planet in the solar system, possibly over 1,600 major ones. Its entire surface appears to have been resurfaced by massive volcanic eruptions about 300 to 500 million years ago, based on crater counting studies. And there's increasing evidence from recent spacecraft missions that some of those volcanoes may still be active today. But perhaps the most remarkable volcanic world in the solar system isn't a planet at all. It's Jupiter's moon Io. Io is the most volcanically active body we know of. It has hundreds of active volcanoes, some of which eject plumes of sulfur and sulfur dioxide hundreds of kilometers into space. The entire surface of Io is constantly being resurfaced by volcanic deposits, which is why it has almost no impact craters. Any craters that form get quickly buried. Io's volcanism is driven not by internal radioactive heat, like Earth's, but by tidal heating. Jupiter's enormous gravity, combined with the gravitational tugs of the other large moons, constantly flexes and squeezes Io's interior, generating heat through friction. It's like bending a paperclip back and forth. It gets warm. Io is being kneaded by gravity itself, and the heat from that kneading powers its relentless volcanism. Now, let's come back to Earth, back to the present day, because there's one more chapter of the volcano story that I think is worth spending some time with, and it's the one about how we watch them, how we monitor them, how we try to figure out what a volcano is going to do before it does it. Because, as we've seen, the difference between a predicted eruption and an unpredicted one is often the difference between an evacuation and a mass grave. Modern volcano monitoring is a remarkable discipline. It's part geology, part geophysics, part chemistry, part engineering, and part art. Because volcanoes don't give you clean, clear signals. They give you ambiguous, noisy, contradictory data, and your job is to interpret that data under time pressure, with lives on the line, knowing that a false alarm can destroy your credibility, and a missed warning can kill thousands. The most fundamental monitoring tool is the seismograph. Volcanoes produce earthquakes, lots of them, and the character of those earthquakes tells you a great deal about what's happening underground. When magma moves through rock, it fractures the rock ahead of it, generating small earthquakes. An increase in the number and intensity of earthquakes beneath a volcano is one of the most reliable indicators that something is happening. But seismicity alone isn't enough. Volcanoes can be seismically noisy for years without erupting, and sometimes eruptions happen with very little seismic warning. So scientists also measure ground deformation. When magma accumulates in a chamber beneath a volcano, it takes up space, and the ground above it bulges. This swelling can be measured with exquisite precision using GPS receivers, tilt meters, that detect tiny changes in the angle of the ground surface, and a technique called INSAR, interferometric synthetic aperture radar, which uses satellite radar to measure ground motion over large areas with millimeter-level accuracy. The bulge on the north face of Mount St. Helens, the one that grew by 150 meters before the 1980 eruption, was tracked with these kinds of instruments. Modern systems are far more sensitive and can detect inflation and deflation at volcanoes around the world from space. Gas monitoring is another crucial tool. As magma rises, it releases gases, and the composition and quantity of those gases change in characteristic ways. Sulfur dioxide is particularly useful because it's abundant in magma and rare in non-volcanic environments. So a spike in SO2 emissions is a strong signal that fresh magma is approaching the surface. Carbon dioxide is trickier because it's released from magma at greater depth than SO2 and can also come from non-volcanic sources. But tracking the ratio of CO2 to SO2 can give you information about how deep the magma is and whether it's rising. Scientists measure these gases using ground-based spectrometers, airborne sensors, and satellite instruments that can detect volcanic gas plumes from orbit. Thermal monitoring, using infrared cameras and satellite thermal sensors, can detect changes in the heat output of a volcano. If a volcano's surface temperature starts rising, or if new hotspots appear near the summit or on the flanks, that can indicate that magma is getting closer to the surface, or that heated groundwater is migrating. And all of these data streams, seismic, deformation, gas, thermal, are integrated and analyzed together, because no single data type tells the whole story. It's the pattern, the convergence of multiple indicators, that gives scientists the confidence to make forecasts. And yet, despite all of this technology, predicting volcanic eruptions remains profoundly difficult. Volcanoes are complex systems with enormous amounts of uncertainty. Every volcano is different. The same signals that preceded one eruption at a particular volcano may mean something different at a different volcano, or even at the same volcano at a different time. Sometimes all the indicators are screaming, and the volcano does nothing. Sometimes an eruption comes with almost no warning at all. Volcanologists talk about failed eruptions or non-eruptive unrest, cases where magma rises, the mountain inflates, earthquakes increase, and then everything just quietly stops. The magma stalls, solidifies, and the volcano goes back to sleep. This has happened repeatedly at well-monitored volcanoes, and each time, the scientists who raised the alarm face criticism, even though they made the right call based on the information they had. It's an impossible position in some ways. If you warn people and nothing happens, you're an alarmist. If you don't warn people and something happens, you're negligent. The eruption of Nevado del Ruiz in Colombia in 1985 is a haunting example of what happens when warnings go unheeded. Scientists knew the volcano was active and had warned of the danger of lahars, volcanic mudflows, which were particularly threatening because the volcano was capped with glaciers that would melt in an eruption. A hazard map had been prepared showing the town of Armero directly in the path of a potential lahar. The eruption happened on November 13, 1985. It wasn't even a very large eruption, but it melted the summit glaciers, generating massive lahars that traveled down river valleys at high speed, reaching Armero in the middle of the night. About 23,000 people were killed. The hazard map had been accurate. The warnings had been issued, but a combination of poor communication, bureaucratic paralysis, political reluctance, and sheer bad luck meant that the evacuation never happened in time. It's one of the most tragic cases in the history of volcanic disaster, and it underscores the painful truth that scientific knowledge, by itself, isn't enough. The science has to be communicated, it has to be believed, and someone has to have the authority and the willingness to act on it. That's what makes the Pinatubo story so remarkable, by the way. Everything that went wrong at Armero went right at Pinatubo. The science was good, the communication was clear, the hazard map was shared widely, the video of pyroclastic flows was shown to decision-makers, the military commanders at Clark Air Base listened and evacuated. The Philippine government acted, and thousands of people who would have died are alive today because of it. It's proof that the system can work, that science and communication and political will can come together and save lives. But it requires all three. Remove any one of them, and the equation falls apart. And this is something that weighs on volcanologists today as much as ever, because the number of people living in the shadow of active volcanoes is growing, not shrinking. The population of the world has more than tripled since the eruption of Mount Pelée in 1902. Cities have expanded up the slopes of volcanoes that haven't erupted in living memory. Naples, one of the great cities of Europe, a metropolitan area of over 3 million people, sits right in the shadow of Vesuvius, the same volcano that destroyed Pompeii. Vesuvius last erupted in 1944, a relatively small eruption during World War II, and it will erupt again. When it does, the evacuation challenge will be enormous. Plans exist. They've been debated and revised for decades, but whether they can be executed in time, for millions of people, in a densely built, heavily trafficked urban area, is something no one can be fully confident about. Similar situations exist around the world. The population of the greater metropolitan area around Mexico City, one of the largest cities in the world, lives within range of Popocatépetl, an active stratovolcano that has been erupting intermittently since the 1990s. In Indonesia, the most volcanically active country on Earth, over 130 active volcanoes dot an archipelago of more than 270 million people. The island of Java alone, home to about 150 million people, has dozens of active volcanoes. In the Philippines, in Japan, in Central and South America, in East Africa, the story is the same. Growing populations, expanding cities, and volcanoes that will, sooner or later, do what volcanoes do. And so the work of monitoring, predicting, communicating, and preparing continues. It's slow work. It doesn't make headlines except when it fails. It requires sustained funding, international cooperation, training of local scientists, and public education that reaches communities who may speak different languages and have different relationships with the natural world. Organizations like the USC's Volcano Hazards Program, the Smithsonian Institution's Global Volcanism Program, which maintains a catalog of every known eruption on Earth, FIVOLCS in the Philippines, the various volcanological observatories scattered around the world, from Sicily to Iceland to Ecuador to Japan. These institutions are the quiet infrastructure of survival. They're the reason we know as much as we do, and they're the reason that, despite growing populations and growing risks, the average death toll from volcanic eruptions per decade has actually been decreasing over the past century. Better monitoring, better communication, better preparedness. The science works. When it's supported, when it's listened to, when it's given the resources it needs, the science works. Let me tell you about one more eruption, and then we'll let the night settle in. This one is recent and small, and nobody died, but I think it captures something essential about how volcanoes live alongside us in the modern world. In March 2021, a volcanic eruption began on the Reykjanes Peninsula in southwestern Iceland, near the town of Grindavik, and not far from Keflavik International Airport, the main gateway into and out of Iceland. The eruption site was at Fagradalsfjall, a low, nondescript mountain that hadn't erupted in about 800 years. The eruption was preceded by weeks of intense seismic activity, thousands of small earthquakes, some of them felt as far away as Reykjavik, the capital, about 30 kilometers distant. The ground deformed as a dike of magma pushed horizontally through the crust at shallow depth. Scientists tracked it in real time, using their seismic and GPS networks, and predicted, with remarkable accuracy, roughly where the eruption would break the surface. And when it did, it was, by volcanic standards, gentle. A fissure opened in a remote valley, and basaltic lava began to pour out, slowly, steadily, filling the valley floor. No explosive blasts, no ash clouds, no pyroclastic flows, just lava, flowing across an unpopulated lava field. And because it was accessible, because it was near Reykjavik, and because Iceland has a culture that's deeply comfortable with volcanic activity, thousands of people hiked out to watch. They sat on hillsides and ate sandwiches and watched the lava flow in the valley below. Some people cooked hot dogs on the edges of cooling lava flows. Drone footage of the eruption went viral. It was, in a strange way, beautiful. A gentle exhalation from the earth, in a place prepared for it, observed by people who understood it. The eruption continued off and on for months. More fissures opened in the following years, and later eruptions on the Reykjanes Peninsula were more threatening, with lava flows moving toward the town of Grindavik and forcing evacuations. The Blue Lagoon, that famous geothermal spa, had to close temporarily. Infrastructure was damaged. The situation reminded everyone that even in Iceland, where volcanic preparedness is woven into the national culture, eruptions are unpredictable and can threaten communities. But the response was measured, informed, and effective. People evacuated when told to. Scientists communicated clearly. The government invested in barriers and monitoring. It was, in its quiet way, an example of what living with volcanoes can look like when all the pieces are in place. There's something else I want to mention about the community of people who study volcanoes, because I think it says something important about human nature. Volcanology is a field where the people doing the work put themselves in danger. Routinely, they hike up active volcanoes. They collect gas samples from fumaroles that could release lethal concentrations of carbon dioxide or hydrogen sulfide without warning. They set up monitoring equipment in places where pyroclastic flows could sweep through with no notice. And some of them have died doing it. David Johnston at St. Helens. Maurice and Katia Kraft, the legendary French volcanologist couple who spent decades filming eruptions at incredibly close range, producing some of the most stunning volcanic footage ever recorded, and who were killed in 1991 by a pyroclastic flow at Mount Unzen in Japan. They knew the risks. They kept going. Not because they were reckless, though some of them certainly pushed the boundaries, but because they understood that the data they gathered, the observations they made, the footage and measurements they brought back, could save lives. The knowledge gained from close observation of eruptions is what allows future hazard maps to be drawn, future evacuations to be ordered, future lives to be saved. Every volcanologist who goes into the field carries that equation with them, the risk to themselves weighed against the potential benefit to everyone else. And in a way, that's the whole story of humanity's relationship with volcanoes, compressed into a single profession. living close to the danger, because the rewards, the knowledge, the fertility, the resources, the sheer fascination make it worth the risk. We've always made that calculation. The farmers on the slopes of Vesuvius are making it right now. The people of Grindavik, who watched lava flows approach their town and then went home when it was safe, are making it. The scientists on the rim of Kilauea's caldera are making it. It's a deeply human choice, and it speaks to something fundamental about our species. We don't run from the things that fascinate us, even when they're dangerous, especially when they're dangerous. And maybe that's the thing to hold on to as you lie here tonight, thinking about all of this. Volcanoes are not going away. They are a fundamental part of how the Earth works, a necessary consequence of a planet that is alive in the geological sense, a planet with a hot interior and a dynamic surface, a planet that breathes and shifts and remakes itself continuously. The same processes that create the danger also create the conditions for life. The same heat that drives eruptions also drives the plate tectonics that recycle carbon and regulate climate. The same ash that buries cities also enriches soil and feeds civilizations. The same water vapor that erupts from volcanoes is the same water that fills the oceans, that falls as rain, that you drank today. We live on a volcanic planet. We always have. The air you're breathing was exhaled from the Earth's interior over billions of years. The ground beneath you was shaped by forces that are still at work. Right now, as you listen to this, somewhere in the world, a volcano is erupting at this very moment. Probably several, actually. Kilauea might be erupting in Hawaii. Etna might be sending up an ash plume in Sicily. A submarine eruption might be building a new seamount somewhere along the mid-Atlantic ridge, unseen by anyone. The Earth never stops. And here's something I think is worth carrying with you. For all the stories of catastrophe, for all the Pompeius and the Saint-Pierres and the Armoros, the relationship between humans and volcanoes is not fundamentally one of fear. It's one of coexistence. People have always lived near volcanoes, knowingly, willingly, because the benefits, the soil, the heat, the minerals, the water, are too valuable to walk away from. And as our understanding has grown, as our ability to monitor and predict and prepare has improved, that coexistence has become safer, not safe. Never completely safe, but safer. And getting better, year by year, eruption by eruption, as each new event teaches us something we didn't know before. Volcanoes remind us that the Earth is not a static backdrop to human life. It's an active participant. It has its own rhythms, its own timescales, its own energies. We've only been here, in the grand geological scheme, for the blink of an eye. The volcanoes were here long before us, building the atmosphere we breathe, filling the oceans we sail, laying down the soil we farm. And they'll be here long after. That's not a frightening thought. It's a humbling one. And there's something deeply restful about it, actually. The knowledge that the world is older and larger and more powerful than any human concern, and that it carries on, reliably, persistently, following the same slow, patient physics it always has. So as you settle in, as your breathing slows and the edges of the day dissolve, think about the Earth beneath you. Think about the heat rising slowly through kilometers of rock. Think about the tectonic plates shifting imperceptibly, a few centimeters a year, rearranging the map on timescales no human can perceive. Think about the magma, deep and quiet, in reservoirs that won't erupt for centuries or millennia. It's all happening right now, all of it. The same processes that built the world you woke up in this morning. And there's something almost comforting about that constancy. The Earth doesn't rush. It doesn't worry. It doesn't hurry. It just moves, slowly, patiently, relentlessly, the way it has for 4.5 billion years. And right now, it's carrying you. The same rock, the same heat, the same restless planet that forged the first atmosphere and filled the first oceans is right there beneath you, solid and warm and endlessly busy, in its own slow, geological way. You're resting on the skin of a living world, and it's a good place to rest. So let that thought settle. Let the weight of the blankets find you. Let the long, slow story of the earth, with all its fire and patience, carry you gently into sleep. The volcanoes will still be here in the morning. They'll still be doing what they've always done, quietly, patiently, building and reshaping the world, one eruption at a time, while you rest.